and we'll go to the lab. But before we do those things, we're going to do a little finite element analysis for the last question on session 10. So in this case, we have a shaft that we're saying is part of a drive axle. Okay, and it's maybe a little bit confusing, but we're just really looking at the parameters involved with this shaft. Okay, and the torque. So we're really, what we're trying to simulate is essentially just this, okay? And we have a torque. If we say this is coming out, we have a torque applied here. We have a radius. C, which we'll call 3 centimeters. And we have a length equal to 1 meter. Okay, and this torque, I guess, is 1150 Newton meters. Okay, and our goal is to be able to figure out what the shear stress might be associated, or the maximum shear stress associated with this, at least on the outskirts of the surface of the cylinder, and also get an idea of what the angle of rotation is of the whole shaft, at least from the fixed end to the circular end, okay, or to the free end. So to do this, we're going to first create our geometry in FreeCAD. And we'll start by creating a new object, and I'll try to bring this in a little bit better. Okay, and we can go to part, and we can click on the cylinder, and then click on that cylinder, and the radius we're going to say is 3 centimeters, so 30 millimeters. And the height we're going to say is 1 meter or 1,000. Okay, and we can then set things up as such. Okay. If you like, you can, and sometimes I've had issues with translating between the coordinate axes in FreeCAD and pre-POMAX, but if you like to rotate your cylinder, you can go to the part design, and then you can go to the model tree. You can click on the cylinder, and you can right click, and you can do a transform. And this actually, I think it defaults to be like 15-degree increments, but you can put it in at 90-degree increments. And you can't see it, I'm sure you cannot see it there. This is X, and then Y and Z is vertical. So X is in this direction, Y is in the green direction, and Z. So if I come over here and I click this ball, it then rotates at 90 degrees. I hit OK, and I can then go ahead and do an export. So we'll do an export to the sessions, and we'll call it drive shaft, and today is 24/06/12, like that. So that's the geometry, and then we'll go to pre-POMAX. Okay, and this, remember, it's just an executable that is somewhere on my computer, and it's in this folder. All right, it's in my download still, actually. Okay, but I can go ahead and run it or open it. I guess I could run it as administrator as well. I don't think it should make much of a difference. And we wait for this to come up. As we see here, it's got, my computer has a lot going on. I'm wondering if I can make its life easier. Maybe I'll shut off, I'll go ahead and close FreeCAD. That might help a little bit. Sure, we'll go ahead and save the file. What do we call this? Okay. I'll close that. And maybe I'll get rid of this as well. Close this as well. Or not. Oh well. Okay. So here we are. And we'll go ahead and create a new. Model. So we're going to use meters, kilograms, seconds, Celsius. And we'll go ahead and import our drive shaft that we made just a few minutes ago. And you can see it was in the X direction in FreeCAD, but it's in the Z direction here. It's not that big a deal. It's just something that we should note. We're going to go to geometry, part, transform. We also can see that this is about, well, it's about 1,000 meters, okay? But we wanted it to be 1 meter. So once again, we go ahead and we transform everything or scale everything by 1/1000th. Close. If you apply it again, then it will make it even smaller. And so now, once again, we're at about 1 meter for, you can see that, right? That we're about 1 meter long, and we are hopefully about 3 centimeters. In radius. We're about, we're close to 6 centimeters, okay, in diameter, right? Does that sound good? Okay, so what do? Next, we can go ahead and we can look at our mesh setup, and we're going to click on meshing parameters, and we can click on the part, and we're going to, let's try this. We'll do down to, I hope this won't kill things. Well, we'll start big. We'll start big and then we'll work our way down. Okay, so we go to mesh, create mesh. Okay, so you see that's kind of ugly. All right, so let's go ahead and we'll undo. And then go to our meshing parameters, and let's reduce this down to maybe 1 centimeter. I think that's even probably too ugly, but that's okay, it's fast. No, that's pretty good. That's pretty good. We'll take that. okay? So from here, what we want to do is a couple of things. This is a little bit different. So first, we're going to create a reference point. So right click, whoops, that's on surface. Create. And this reference point, we're going to want to put it out. Oh, okay, that's interesting. It's putting that right there. Interesting. That's not, is that the origin? Okay, so we're going to play around a little bit here. It's going to be on Z, so I wanted to do like 0, 0, 1. Let's see where 0, 0, 1 puts us. Okay, 0, 0, 1 put us way out there. So let's do the following. Let's do, I guess it's fine. We can change it. Or we can do, well, because it's, Z is coming out that way, we'll go ahead and do 0, 0, 0. Okay. So that's a reference point. And then we are going to constrain this. Okay, reference point. Okay, to the surface that it's on. Okay, so we click there and we click surface, and now it's constrained. Okay, why are we doing this? A couple of reasons. One, we want to know the rotation, okay, at that end, and so pre-pull max will tell us what the rotation is of that point. We'll show you how to do that in just a couple minutes. And then two, we want to apply a moment to this system, and it's nice if you can apply that moment right about a certain axis at a given location. And so now that moment is being applied, well, we're going to apply that moment to that point. Okay. And it's tied to that surface, so everything will go nicely. In fact, in the last example where we had, I applied a pressure to create the force, we could have actually done this as well. We could have tied a point to that surface to which we applied pressure, and that would have been able to give us an opportunity to then apply concentrated force. Anyway, okay, so I've lost my marbles. Not really. I've lost my spot. So here we go. We're going to do elasticity, right? And what did they say? What did I say? The question here. So nu is 0.3 and the elastic modulus is 200 gigapascals. All right, so let's go in 200 GPa and wait, did I say 0.3 or 0.2? I can't even remember. 0.3, good. And so now that's okayed. And now we can create a section. Remember, we'll do a solid section on the whole part. Hit OK. All right, and we need to add step. So we're going to do statics again. We'll hit OK. And now, we want to add a fixed constraint on this end. So to do that, right click here, boundary condition, fixed. We'll do a surface right there, hit OK. Okay, so it's fixed. And over here, we're going to apply concentrated torque or a moment. Okay, and we're going to do that at a reference point, and it knows there's only one reference point, and so that's it. Now, it's a little bit tricky here, but you see that we're going about the z-axis. Okay, you see that? So what we're going to do You know, the perspective and various things make it sometimes a little bit tricky. But you see that z-axis, for our intents and purposes, is coming out of that face, even though we put it at the origin. Okay, and actually the fixed thing is like 1 meter back. It's actually -1, or negative 0, or 0, 0, -1, if we were to think of it in terms of coordinates. So let's put in the torque that was specified in the problem as 1150. Okay. Hit OK. And did I put it in the wrong spot? Ah, yes, I did. Okay, so I can do, well, there are a couple of ways, but I'll do it here. Okay, let's try that. There, now it's coming out. Okay, is that good? All right, and then for history output, we're going to create something about I want it to be reference point. Okay, so we're going to do the node that's essentially very close to that point. Okay, the reference point will be there. Okay, and then we'll hit OK, and so that will give us a history, and then we can run analysis, and hopefully this will work. Sure. You haven't done anything yet. Okay, so let's take a look at the results. All right. So it looks nice and colorful, but what does it mean? Well, the displacement is a little bit confusing here, right? There's going to be displacement. I mean, this, how do you say this? U1, U2, U3, right? Those are linear displacements, right? And all would be the magnitude of U1, U2, U3. So it's going around and it's looking and saying, oh, you're twisting, so some of these points are moving, right? And what's the maximum displacement between where it was originally and where it is now? That doesn't necessarily tell us everything we want to know about rotation. But let's start with something that we will understand. Okay? But this is a little bit confusing. Okay, so let's talk about it. Looking down this way, and maybe I'll do a view. Let's see. Let's do a standard view, front view. All right, that's great. Okay, so now there's no mistaking. This is z coming out, x to the right, y to the top. Does that make sense? All right, so what is, if I want to know something about the stresses, okay, I've got y this direction. No, I have x that direction, right? Let me just correct. Yeah, x, y, z. Good. Okay, I've got x coming out this way. I've got y going that way, right? And I've got z coming out of the board, right? So z is coming out of the board. If we're interested, we said, right, yippee-yi-yay, that tau is t C, and J, correct? But how do I figure out what T, C, and J are? Or not T, C, and J. How do I figure out what tau is in this system? Okay. So for example, what are tau xy? What is tau yz? And what is tau, we'll do xz. Okay. Well, remember, the first subscript is what? That's the face it's acting on. Second subscript is typically the direction. Okay. So, which way is the shear stress? I mean, first off, right, it's going to be kind of on these surfaces, right? Like you can't really see them, right? But it's, and I twisted about Z, right, in the positive. So it's kind of like, I've got shear stress kind of like going that direction, right? Kind of going around the system like this. Okay. So, you tell me, where is tau xy? Where would be a good place to draw tau xy? Yes.
So on the right side,
Yeah, okay. Okay, yeah. So there's going to be a shear stress I could draw as tau xy there. Okay. Now, maybe it's good to take another screenshot and we'll do something a little bit like this. Okay. And let's look at what you just said. What we said, tau xy, one place to draw is on this right side going up. So what is tau xy? Tau xy is not S11, not S22, but it's yes, it's S12, right? Okay. So here, okay, we could see that this face over here, this is the X face, and it could be moving up. Now, this is just showing the max. All right. What I can do is I can kind of come over here approximately. Okay, and you can see that it's doing, I can like kind of do queries over here. Okay. All right, so that should be giving us a stress. Okay, and that stress is actually really small. Hold on, something's not right. It should also show, oops. Okay, yeah, because the calculation here, okay, that we, if you do the calculation just by hand, that should be 27 megapascals. That is not what we're seeing right here. Okay, so what is going on? We see a much smaller value. That's like, 27 megapascals, that's, 2.7 times 10 to the 7th. This is minimal. What is going on here? So it has, okay. that is closer to what we want. So, and this is also, okay, so this is also closer. All right, so yeah, why is that one so small? What is going on here? Okay, so this is tau. Okay, well, maybe I'm doing something wrong. So let's see. If we come back to this, all right, with x, so tau, so this should be what pre-Pomax calls sigma 1, 2. This should be what pre-Pomax calls sigma 2, 3. And this should be what pre-Pomax calls sigma 1, 3. Okay, so sigma 2, 3, okay, would be on the y face, so something here in the z direction. So that would be something coming out like this, or coming out like this. That would be the sigma 2, 3. Okay. And sigma 1, 3, okay, x, sorry, that's on a y face. Yeah, that's right. So y face up there. That's a sigma 2, 3. And sigma 1, 3, yes, would be, for example, on an x face coming out. Okay. So let me take another screenshot. And let's bring this in. I'm going to delete this one. Yeah, that's getting higher. Yeah, so up here, something is interesting with the optics. Okay. Yeah, we'll say we'll do that one. All right, so let's bring this in. Like this. Okay. So in this case, oh, I didn't have the axis in there, but that's okay. Right, x is that direction, y is kind of up, and z is still out. Okay, so x y and z coming out. That's kind of how it is. All right, and this is, we're looking at sigma we're looking at the sigma 2, 3s. So this is sigma 2, 3s, or sigma y, z. Okay. So if we had an element, say on this face, like this, okay, then we would say that the shear stresses, okay, would be coming out of the z face on this side, and that would be sigma 3. And if I were interested in going this direction, that would be the x minus x. Okay, so this, or if I'm on, so this would be like that, would be sigma or tau 3 and then minus 1. Or I could draw it this way, which is probably better, tau z x. Okay? If I'm interested in that. So that's what this one is too. Those are the tau z x's. So those are the sigma 1 3s. The shear stress on over here, this is going to be an x. No. Yeah, that's z, and that's in the x direction. That's right. That's correct. Right, so then these stresses would be like that as well. Okay, and then over here, if I'm interested in the stresses, I have like an oblong shaped element on the side. Okay, that would be, for example, a z face. Okay, and in a y direction. So this would be sigma or tau 3 3 2 or tau 2 3. Okay, like that. Okay, so I agree that this is going to be high. This is a sigma 2 3. Okay, so it's high there. If we have a sigma 1 2, so okay, so what happened? What did I do wrong? Sigma 1 2. Okay.
So I think it has to do with the coordination system for control max. I think what it does, it sets like 1, 2, and 3 aren't necessarily x, y, and z. I think it's first axis, second axis, and third axis, and depending on the geometry you import from, it assigns the variables based on that.
It should be, but since it's drawing 1 2 3, or since it's drawing x y z, it should be aligned. Like 1 should be x, y should be 2, z should be 3.
So I had problems with my homework. When I imported it along the z-axis, in order to get the x strain or whatever, I had to pull the 3 3 because it was running. I forget how it was, but yeah, it was running like if I wanted the x value, even though it was running along the z-axis, I had to pull that like s3 3.
Okay. That would make sense. Maybe there's a bug that was introduced in this version, because I don't remember this happening before. Okay, and in fact, I tried to rotate the cylinder into X, and now it's coming out in Z.
Yeah.
And I'm getting confused about what is what here. Okay, so I apologize. I'll try to take a look at this and send a message here.
Yeah, if you use right hand rule and reassign it to Y, Z, and X as 1, 2, and 3,
yeah,
it should work out. It's weird. Yeah.
Okay. So you're saying that. All right. So we'll have to table this and come back. I apologize here. Okay. So, yeah, because something is very strange. But this is, I'm more inclined to think that I did something wrong than the software. That's usually my assumption, all right? So if we come back to here, this is an X face But is that on the object? Yeah. Okay, so see that? Okay, I think that this is now working out correctly. All right. What we have to do is we have to draw an element on the surface, okay, that is corresponding to something that like you would have on the surface. So, for example, let's just do this again. And I'm sorry we're taking too much time on this, but it's kind of, I think, important to understand. Okay, so let's go ahead and we'll do that. Okay, so this one is going to be, okay, so this is showing legend for S13, okay? And in this case, just like this case, we have Y coming kind of upish, X kind of this way, okay, and Z kind of this way, all right? And in this case, I'm going to draw, I have to draw an element. Let me choose a different color so we can see. Green is not the best. Purple, black is actually probably pretty good, all right? So black element like that, okay? That element has to be on the surface of the material. And now, if I look at the element, okay, what directions do I have here? I would say that, and we're looking at S13 here, okay? If I have this, let's say I had a stress coming out, oh, so you can't see that. Oh, I can just do black again. The stress coming out of that face, we agree that would be sigma z, okay, if I had an element. And the stress coming out of this face would also be sigma z. The stress coming out of this face would be sigma x, okay? The stress coming out of this face would be the opposite. And the stress coming orthogonal out of the thing, that would be sigma y, all right? So now I've got a z face, all right? And the x direction, this one will be we'll say tau, and this is going to be zx. Do you see that? Okay, it's on the z face in the x direction. Okay, and once I know one, I know the rest. Okay, because they have to whoops. Line up. Okay, you see that? Now, tau zx is equal to tau xz. Remember we discussed this? Okay? And in this case, we know the torque. Let me find a different color that will work. Is being applied in that direction. Okay? And remember, the way to think about this is in terms of twists and what's happening with the deformation. So if I look at this element up here, I would say with this torque being applied, the element should be getting morphed so that this side moves like this relative to the other side. Do you see that? Right? Because as I'm further along, right, that thing is getting twisted. It's getting twisted, and this is getting pulled this direction. Okay? Does that make sense? This is closer to this end. This is closer to the wall. So this deformation, so this is just using my intuition. Whoops. Okay, this is using intuition. Okay. Which means that the actual magnitude of the stress is going this direction, like from this side to that side. So it's actually negative Zx. Okay? So the stress, what do we get? If we look, this is, remember, S13, right? This is essentially tau x z. Okay? So what is the value of tau xz here? It says it's minus 2.3 megapascals. At least where I selected, right? So it says that tau xz is equal to minus 23 megapascals. All right, and that lines up with reason. There must be questions on this because I was confused a few minutes ago. Do you see how this is working? Any questions on the geometry? Okay. So if I pick a different point, I can find something that's more maximum. You see, as I move around the cylinder, I no longer have a nice tau xz or tau zx aligned with the element. Okay? It's going to be like a different, it's going to have a rotation involved with it, right? So if I come back over here, all right, and I query, well, I can see if I get to the dark blue, okay, here, for example, just a little bit over, okay, I get a minus 27, essentially. Okay. Now, let's say that we rotate around. And Eric, I'm not going to deny that I think something weird is happening, but I think it's less weird than I thought it was. All right, so let's say now, okay, you see I've got x facing up, z, and I've got y going this direction. All right, this value is a lot less. All right, and down, and in fact, we should be able to get, or maybe around here. So I'm looking at where does it go to 0, or close to it, right? So if I like query over here, okay, that's still, and this is, maybe I need more elements to be more accurate. Let's see here, if I do this one, that's negative. Yeah, so it goes very quickly. It goes, yeah, so this is 6 to the 4. This is pretty small right here. 5, so all times 10 to the 5th. 10% of the 6. There, that's a small one. Okay, so let's get rid of these other ones. Oh! What did I just do? Oh, that was painful. Oh no. Oh, I just lost the whole. You gotta be kidding. Oh, I just lost it. I'm so upset. But anyway, the point is, if I rotate this, right, I can get a different element that's up at the top, right, that I can draw. And then I would have like my S1, where I have my like S23, okay? And then I should see when I click on S23, I'll get a very high value of 27 megapascals, okay? I'm sorry for the delay. Let's go, let's go. So, yes, so for this assignment, the question, oh, I have to tell you one other thing. Okay. I have to tell you about the strain. Man, I better get it to run again. Oh, no. Yeah, I had to tell you one more thing because it's asking about the microstrain. Let's see here. We're going to do. Okay. All right, so we were just looking at the strains. All right, and we just talked about how we had our nice, actually this one is the one we were looking at, tau xz, all right? Do you remember how to relate shear strain to shear stress? Shear strain to shear stress?
With the shear modulus?
Yeah, this is the shear modulus, right? So one thing we can recall is that tau is equal to g, right? And the finite, we did imply, we put in an e and we put in a nu, right? And so it was calculating this out, okay, like this. And here, we've been showing so far what the shear stress is, but we can also have the finite element analysis tell us what the shear strain is. There's a little catch though, okay? And it'll come out a little bit more when we do the Mohr circle for shear strain, but and regular strain. What pre-POMAX and some softwares do is they use a tensor form for strain. And this tensor form, right, you can see epsilon is equal to epsilon 1,1, epsilon 1,2, right? You can see all these different components, right? And we can then put epsilon xx, epsilon xy, right? And epsilon xx is just epsilon x. And we see that if we have normal strains, which you did before, okay, these normal strains, if you look at this matrix over here, they're just the same as your normal epsilon x, epsilon y, epsilon z. But because of the way it does tensor math, the off-diagonal terms are actually twice what, or they're half, sorry, of what the real strain is, okay? So what we had to keep in mind is that pre-POMAX uses tensorial strain. So epsilon x is still equal to epsilon 1. Right? Epsilon y is still equal to epsilon 2. Epsilon z is still equal to epsilon 3. Okay? But the off-diagonal terms, so like epsilon xy is equal to 1/2. So epsilon xy is equal to 1/2 gamma xy. Okay, so if I click on, and this, right, this is really epsilon 1, 2. If I click on this value, I'm going to get half of what it is. So I had to multiply to get that. Okay, so if I ask, in the homework, we ask you, what is the shear strain, or what is the maximum tensorial shear strain in microradians? This means true shear strain divided by 2. Okay, so we're saying, tell us what is the true shear strain, or yeah, we're actually, we're just asking for the tensorial one. We're asking for this. So we're asking for, say, maximum of these guys. Right? That's what we want. All right. So if we go back to pre-POMAX, the way you do this is you go to strain, and we can go. We have an inkling now that it's going to be epsilon 2, 3 or epsilon 1, 3, because those were the shear stresses that were maximum. So then we can come over here, say that epsilon 2, 3, and we look, okay, what are the maximums? And we come do a query over here. Okay. And we get something. These are looking kind of like the maximum. So let's say that's 0.00018. So I'm going to click there. I'm going to call that good. All right. And this is like we said, this is a 2-3, right? It's telling us 2-3 strain. This value should be about, or something like half of the actual gamma. Do you see that? The gamma was 352 microradians, and this is 176 microradians, and what we just measured was 181 microradians. Okay, so this is in the ballpark, all right, of what we have to report. Okay, so this is strain 2, 3, like that. Okay, and we're saying that this is like 181 micro, or yeah, microradians. Okay, because remember, this is an angle. Before we just reported it, I mean, radians are kind of dimensionless anyway, but before we just reported it in terms of microstrain, because that was normal. Here we report it in terms of an angle rotation. Okay. Questions, thoughts, concerns? You're like, how in the world am I going to get this right if it just took us this much time? Confident. What you got to do, okay, is you've got to calculate out what the appropriate epsilon is, right? And so the appropriate epsilon is going to be half of what your gamma is. You can calculate. How do you calculate out gamma? Right? How do you calculate out gamma? Well, the way I do it is I do TC over J, and then I divide it by G. So it's really TC over JG, right? And that's how I would calculate the gamma. it's going to be the maximum at the radius c. And then after I've done that, then I would start hunting around to see something that's half of that value. Okay, and then that's what the screenshot should be. Okay? Okay, we got to go on. Here's your mouse back. Thank you very much. Okay. Set my computer. Sure. All right. Session 11, beams. This will be a little bit of a review, and you only have like 2 very simple questions. Okay, so you're going to be happy. The homework, the main part of the homework tonight will be getting the pre-prom axle. Okay. So today we're going to talk about how we can approach beam bending problems. We'll talk about the shear moment diagrams, and we'll talk a little bit about a graphical method to construct them. And this will probably look somewhat, actually should look very familiar. Okay, so what are the things that you'll be able to do? You'll be able to calculate relationships for the axial twisting along a beam. No, with transverse loading, we're not talking about that. Okay, so not this one. Axial twisting is interesting. That's not this. Calculations of internal shear force along a beam with transverse loading. Yeah. Calculations of the internal bending moment along a beam with transverse loading. Yes. All right. And we'll know something about relationships between the distributed transverse force and transverse shear force. Yeah. So beams are long, slender members, okay? And you're like, yes, I remember this from statics. There are different types of loads, though, that you can have on a beam. You can have a point load, okay, or a concentrated force at a given location. You can have distributed loads, which, of course, you probably rather not have, okay? You can have different types of supports. You can have simply supported, okay, with one end that is kind of pinned and another with a roller. Often I make mistakes and I do 2 pins, and we even say like pin-pin type of configurations sometimes, but these are simply supported, more correctly stated, and you can see you have 2 concentrated forces, and then the infamous cantilever, right? And of course this has reaction forces on it, and it has a moment reacting as well. And we can even have things called an overhanging beam, which has the same things that you have with a cantilever, but now you have an additional transverse force. Okay, so we've seen these configurations too. All right, now if we think about the slice, all right, that we might take. So we're looking at a pizza on a beam, and this one happens to be round. Okay, so it kind of is like pretending that it could also be a shaft. What are the different forces and moments that you can imagine? And this is kind of very similar to what we just talked about. You could have a force F XX, all right, in this direction. So that's coming along. That's an axial force. Typically not super interesting in terms of beam bending, okay, because it's just causing the beam to extend. You could have a shear force. This is interesting and kind of problematic and tricky, right? But you can see just like fxx has two subscripts in this case, these have two subscripts, fxy and fxz, and we're using the same type of nomenclature that we would use when describing a stress. So we have this force x, all right, on an x face, or fxy, x face in the y direction, x face z direction. Okay. You could have a mxx. This is going to be a twisting problem. This is a torsion problem. So not something you're typically going to see mixed with our beams. Well, not exactly. I mean, yeah, yes, you could see it. You can see it. Sorry, you could see it when we do combined loading. We'll talk about this, but it's not. This is not of primary interest for beams. It's more of interest for shafts. This mxy and mxz, those are what we would consider to be the bending moments. Okay. You see that? You see how if the left end is fixed at a wall and you apply that moment, you're going to get a bending, right? This thing's going to kind of bend in that direction if mxy is applied. If mxz is applied, it's going to bend upwards. Okay? And when I say, what do I mean by applied? I think often about what is the external load on the system, right? But these mxy's, mxz's, these are actual internal bending moments. Okay? So they correspond to what's happening externally, but they're the internal ones. Okay? What happens inside the beam? Well, this is where we visualize these internal shear forces and internal bending moments, right? So in this case, what are we interested in primarily? We're interested in fxz, fxx, and we're interested in mxy and mxz. We're less interested right now in mxx because we just covered a bunch of stuff on torsion, and we're less interested in fxx because that would be a bar. Right? So we're shifting our focus. And here we find ourselves drawing these diagrams, which you all love. You love these, right? No, at this point, maybe not, but you're still mechanical engineers. And a civil engineer, sorry. And we have aerospace too, right? Yeah, we have aerospace. So you haven't left the field because of these diagrams, which is good. So we are going to think about how V and M are varying as a function of X. Okay? And we will also have things like, axial loads that we can draw in there, but typically we're interested in V and MV, right? And we have a y-axis, and then Z in this case would be coming out of the board, right? So that's just what we're interested in. And in terms of design, we're going to ask things like where and what quantity do we have maximum shear, okay? And where is the bending moment, okay, the maximum, all right? And maximum shear is, we can have a varying shear force, right? We're talking, I'm saying stress because that's where we want to go, right? But we can, as we make these diagrams, right, we're going to have varying shear forces and varying moments, and where those shear forces and bending moments are the highest, right? Those are the potential hot spots. It turns out for beams, we care more about the bending moments than we do about the shear forces in terms of calculating the whether or not it will break types of things. And also in terms of how much deflection does it have. But we're going to go through both. Okay, we'll go through both in detail. Okay. So, here is another three-pronged approach to statics, but this time applied to beam bending problems. So what are the three pillars? Equilibrium,
It's geometric.
yeah, geometric compatibility, and
Constituent equation.
that's right. So we're gonna spell them out again. Okay. So we're gonna idealize the actual problem. We're gonna create the model. Okay. We're going to use equilibrium externally, and then we're going to do internal equilibrium. Right. So this is an approach, and we have the eventually. Okay. We'll get to the three pillars. Eventually. Three pillars, which are equilibrium, okay, geometry, and constitutive. Okay, but for now, most of what we're doing is going to involve. Actually, it's not going to be till pretty much the end where we're really going to get the constitutive relationships in for indeterminate problems. Okay, so this is kind of right now focusing mostly on equilibrium. So we create a model. So these are another kind of three sections. We do external equilibrium, and then we do internal equilibrium, like this. Okay, so this is more like the equilibrium. I'm sorry, I was getting too excited about the other three pillars, but these are the kind of these were the two pillars, shall we say, of equilibrium. Okay. All right. So come on. Okay. How do we describe the shear and moments across the beam? We use diagrams. Okay. And you have an opportunity, right, to think about this type of diagram where you have a slice, right, and you have the opportunity to think about these diagrams that we've come to love that give us shear force and give us bending moments. All right, so these shear force and bending moment diagrams are these. So we got to relate up to now, right? The primary way of creating these diagrams was to do equilibrium on these types of diagrams, right? But we're going to show you a couple of different ways to do this. And here's another one for the bending moments, or this is shear forces, and then here are the bending moments. Okay, but this is with a concentrated bending moment, right? So. You could do these, and we will do these, all right, based on equilibrium, and we still use equilibrium on these sections, method of sections, quite a bit, and on external equilibrium. Okay, and we've talked about the sign conventions a little bit, but here's another slide on that. So, with a distributed load, up, all right, is actually positive, even though a lot of the distributed loads, right, are down. So those are negative. And this is the classic come out of a face, normal, positive x, right? And this is then the convention that we use for bending moments, right? If you open up and you cover up the right side, then you have a counterclockwise bending moment. If you cover up the left side, then you have a clockwise bending moment. and then the shear forces, okay? If you open up to the right, it's down. If you open up to the left, it's up. Okay, so those are the conventions. These are non-negotiable, right? Everyone got together in the Hibbler world and said, this is the convention we're going to use. Because they're internal and we want to keep them straight. For the bending moment diagrams, right? Otherwise, you would not, when you look at a bending moment diagram, you wouldn't have, you know, you could get the magnitude right, but you wouldn't know which is up and which is down. Okay, but these are Hibbler's conventions. They are not CDL's, Crandall-Dawn-Lardner's conventions, like I mentioned before, the ones that I use, but these are the ones that we're using for this class. External forces, external moments, you have freedom. Okay? But what's cool is you can do whatever you want for the direction on the external lobes, but you're still, once you do the internal calculations, if you follow these conventions, it will get the same thing, right? Because the external lobes will just be minus or positive, but then the internal ones will come out. Okay. So, yeah, it's confusing because sometimes they disagree. This is some powerful stuff right here. These are now going to be two new equations which I do not believe you covered in statics. Okay? And they provide another approach to making bending moment diagrams. Okay? In words, what it says, or what the equation on the left says, is that the derivative of the internal shear force with respect to x as it's moving along is equal to the distributed force. Okay? And the other one is that the derivative of the moment with respect to x is equal to the shear force. Okay? So these are some new relationships, and we can derive these. We will derive these, right? But this is just an opportunity to see these relationships and then apply them. And what you'll hear said is that we're constructing our shear force and bending moment diagrams using this integral differential form. Okay. What does that mean? That means, for example, if I have the distributed force, I can integrate it. Look, I could do Wx dx is equal to dv. If I integrate both sides, then I've got v is equal to the integral of wx, w of x. Similarly, if I have the shear force, I can integrate that, and then I can get the bending moments. Okay. So let's do some derivations. This is using the positive w. So that's, remember, this is the convention we just introduced a second ago. So we have a positive w, a distributed force across the top, and we take a slice of this beam, and we follow our other conventions. All right, what are those conventions? Well, imagine that this is a slice of internally of the beam. On the right side, we have our bending moment this way and our shear force downward. On the left side, we have our shear force upward and our bending moment this way. And we're following our distributed force Wx. Now, we've picked a location O on the right side. Okay, whatever, but we're going to say that this element, this part of the beam has a width of delta x. So that's the location we're picking O. We're going to use that for our bending moment calculations or moment calculations on this element. But x is smaller here and bigger here. So what we're going to say is we're going to have like some x and some x plus delta x. Okay? Or we're going to have a width of this element of delta x. And on this side, okay, generally speaking, if we have a v, we could have said v plus delta v on the left side and v over here. But what we're saying is that there's some small change in the shear force, and there's some small change in the bending moment. And of course, all these terms, except for the distributed force, W, are internal. Okay, I guess I should have probably clarified that. When you have this W, this is a way to relate the outside world to the internal world. So let's do some equilibrium. What does equilibrium look like for forces in the y direction? Someone spit it out. Yes.
V minus parentheses V plus delta V equals zero.
Okay, that's part of
Oh,
it.
plus W.
Plus
Plus W. Yes.
plus W, but that's a distributed force. So plus,
Times W.
you got it. You're on fire. Okay. So we got V minus quantity V plus delta V plus W of X delta X is equal to 0. Okay. And that simplifies. Why? Because the V's knock each other out. And we get that delta V is equal to W of X times delta X. And we get delta V divided by delta X is equal to W of X. And we take the limit of that, and voila, that's our equation. All right, that was what we just showed on the previous slide. So we derived it like that. This goes on your formula sheet, big time. And what about on the what about from the perspective of changing or taking the moments? Here we have the summation of all the moments at a location, we'll call that O, they're going to equal 0. And we have here that we have minus m plus this guy. All right, so remember, a moment doesn't care. If you say you have a moment, it's like you take this screwdriver, you slam it into the beam, and you twist. That twist it don't really care where you put that twist, that torque or that moment from the screwdriver. It's going to apply that moment to the whole system. But if I say, I'm playing on a force at a given location, okay, relative to the rest of the system, then I have to keep track of where it's being applied. And so here, it's a little tricky, right? But you see that W of X is being applied about halfway across this thing. Okay? And it has a magnitude of Wx times delta X, right? So that's the moment, and it's going to be at least relative to this, it's clockwise. So it's going to be negative. And V, all right, is on the left side, and that's a distance delta x, so that's minus v delta x, and we don't care about v plus delta v because it's applied through O. So since it's applied through O, then it's 0. That's one of the things, right? You usually try to put your location where you're going to do your calculation of moments at the most confusing spot. Okay. So then we can do a little bit of math, and delta x times delta x, so small thing times another small thing, all right, is about 0. So we don't care about that. So what do we get? We get just a relationship between the change in the moment and v and some delta x. So you've seen this before. Delta m is equal to v delta x, and the limit is the delta x goes to 0, means that we can write the other big equation that we just had on the previous slide, that dm dx, or dm, the derivative of the moment with respect to x is equal to. So these nice equations can be applied how? Well, let's look at some problems. And we're going to use the differential forms here. Okay, so let's think about the slope of the shear force V as a function of x is equal to the distributed load W at x, okay? And the slope of the moment m as a function of x is equal to the shear force. That's this one. So let's say that you were given this bending moment diagram. And that's nice. Okay, you don't know what it corresponds to in the real world yet. Okay, but this is going to be some type of quadratic. So if I'm interested now in going up, and I have dm dx is equal to v, right? If I integrate dm, right, then I'd be integrating v of x, right? What should this become? This is a quadratic, and if I integrate a quadratic, well, then I would get it to the third. But if I take the derivative of quadratic, right, I am going to get to a first power, right? So let's see. So let's we have to think about this kind of carefully. All right. Another way, right? I probably said it backwards, or another way to look at it is if I take the derivative of this moment, I should get v. Simpler said, right? So, what is the derivative of a function in geometry? Slope, right? That's what we learned, right? So this is a quadratic. If I were to figure out the slope at every one of these points, that would tell me what the shear force is. Okay? So, and let's just say, you know, if it were like x squared plus x plus 1. Now, if I take the derivative of x squared plus x plus 1, what does that give me? It gives me like 2x plus 1. And that's a straight line. So I told you it was a quadratic. Tell you now we have to take the derivative of it. That's what it should look like, a straight line. Okay. The slope here, okay, here, it's always positive. Okay, so that's satisfied here because this is, yes, its slope is, the slope is negative, but the magnitude of the slope of the moment is always positive. Okay? And you could have figured this out. You could have fit a quadratic to this if you had wanted. So similarly, dv dx is equal to w of x. So if I take the derivative of this function, I will get w of x. What is the derivative of that function?
Negative constant.
Yeah, it's just a negative constant. Okay? So that means that we have a constant negative applied distributed force because that's what w of x is. So what does that look like? It looks like that. Okay. All right. Now, we went from kind of an obscure expression upward to an actual physical problem. Right? Often you're going to be given a physical problem and you want to go this direction. Okay, so we can do the integral. Right? The integral form is this. dv equals wx dx. We do the integral of wx, all right, between a and b, okay, like this. And the bending moment can be thought of this way. All right, so this is how you might see it in a textbook. All right, this delta v equals the integral of wx dx. In practice, okay, you're really just taking the derivative, and you can think of this delta v as being vb minus va. Right? There's some offset, or you can think of this delta m as mv minus m. So here we start with our distributed force again, right? And we're doing exactly the opposite, but we would take the integral of a constant that's negative, and we would get a negative slope, and we have to use a boundary condition. Okay? So that's what you get there. The same thing here. You take the derivative of that expression, okay, and you want to know what some boundary condition is, and you can figure out then what the function would be. Okay. So that's how these equations are useful. So the methodology is step one, calculate the external loading. That's a theme, right, that we've talked about. Get the values of the shear at the ends of the beam. Establish the moments at the ends of the beam. Okay, so what do we mean? We're going to talk about how we do this. And then step two is use the differential and integral forms. Okay, and then you can make the diagrams. So first step in this situation is external. So what is F effective? What is the magnitude of F effective? Yeah.
Just L times W.
Yeah, that's right. That's it, right? And we know, where is it acting? At the middle, right? Oh, we're halfway there. All right. And we have our MA and our R. Those are our chosen. We can do whatever we want with those two in terms of the direction. Since the distributed force is acting downward, right, a reasonable guess is to apply the reaction moment upward. Okay, and since there's a bending moment, or since that force is acting and some causes things to go to kind of want to twist this way, right? A reasonable thing is for MA to go against it. Okay. So we now do external equilibrium, just like that, and we get F effective, MA, and we get R. Okay. So we did those things. Now, if we want to start drawing our shear force, okay, we will want to do an integral, okay? And how do we do this? So we're going to say, well, V is equal to W dx, okay, plus C1, all right, so this is, right, indefinite integral, okay, and we have V equals to this, not this, right? We're going to have a, we're not going to have, well, sorry, it is this, okay, but we don't know where it is because we have to pick, hold on, no, yeah, it's that because I made a mistake. Yeah, it's just WX. That's why that's there, and that's, yeah, it's just W naught X, okay? And W naught is a negative value, all right? So we have this plus C1. Now, the question is, how do you figure out where or what's happening at these boundaries? And this is where a little more explanation is helpful. it says here that you should get the values of shear at the ends of the beam. What does this mean? So on the right side, so we have this beam. Okay, and we have R and we have MA. On the left side, well, let's do the right side first. If I do an element just on the right side, so this has no external force acting on it. You see that? It's a free end. So if we use our convention, okay, what is our convention? Coming all the way back here. Right, oh, here it is. Well, this is one. So on the right side, we have the bending moment counterclockwise, and we have the shear force down. On the left side, we have it up. So let's use our convention. Okay, so our convention is shear force up, internal bending moment like that, and there's nothing on the right side. Okay, on the right side, it's 0. So in this case, this would be length L, and this is going to be going from the left side is X. So on the right side, V is equal to 0. Do you see that? On the left side, I take a nice little slice, really, really, really close, okay, to the left side. And here I have R, and I have MA, and I follow my convention, which is down for V, up for M, or counterclockwise for M. And here we have that V is got to be equal to R, but we calculated R previously here, W naught L. So V is equal to W naught L, and well, what is M equal to? Well, M is going to be equal to minus MA, and minus MA will be this minus F effective L over 2. Okay, so at least for the shear, right, what we have is that the shear force is equal to W naught L. So what we do is we draw at the left side W naught L, and on the right side, right, where X is equal to L, we draw that V is equal to 0, and then we just do a line between them, because we know it's a constant slope. Okay, so this is important to be able to do this bit of boundary, bit of internal force, internal shear force and bending moment calculations at the ends. Okay. What about for the bending moment diagram? Well, we go ahead and we integrate again. All right, so now we have an expression. Okay. Oh, and C1 has a value, right? Because if this is 0, so C1 is equal to this W naught L right here. Okay, so C1, right, C1 is equal to W naught L. Okay. So when we integrate, we've got to do this integral plus a new constant, okay? And we got to figure out the boundary conditions. Well, we already did the boundary condition here, or we did the boundary condition at the left. We said that M is equal to M minus MA at the left, right? And MA is this guy. And at the right, we can also say we know what the internal moment is, and this is equal to 0. Okay, so that's what we get here. These boundary conditions, and then we draw the appropriate parabola, okay, because it's integrating the first order system, a line, to come up with a second order system, and we satisfy the boundary conditions. At the left side, it's got to be equal to this minus ma, and minus ma is w naught L squared over 2. At the right side, it's got to be equal to 0, so we satisfy that. Any questions on that? Is that pretty straightforward in terms of how we do this integral with the boundary condition? Okay. So it's about taking these internal slices. Even though step 1 is what we often think of as external, it's actually now including getting the values of the internal shear force and the internal bending moment at the ends. And then step 2 is the integration. Okay, a region with a concentrated force. Every now and then, like you saw the overhang, right, or if you see like 3-point bending, you're going to have a force applied at a given location across the beam. You can do a trick or two. Here it is. Wherever a force is applied, and remember, positive, up is positive, right? So, or y, if it's in the positive y direction, it's positive. Look what happens. If I do my little equilibrium on that little slice, I get that v minus quantity v plus delta v is plus f is equal to 0. So now delta v is equal to f. Okay, and this is going to be in the upward positive direction. So what does this mean? This means that if I've got my bending moment diagram and something's happening, when I get to this point, I have a discontinuity in the shear force, and I jack it up by F. Okay. Similarly, if I have a discontinuity in the bending moment, okay, or with a coupled moment like this, I get a jump in the bending moment. Now, what's weird here, and this is where conventions make a difference, this applied moment looks like it's negative, right? It's going into the board. But the result with the internal bending moment, okay, if we do the equilibrium, means that we have a positive jump in the moment. Okay, and we ignore this v delta x term. You see this? So this mmap is negative, but if I'm going across from left to right, that's the other thing to keep in mind. You see how there's a direction with the x? I'm going over here, I'm starting over here, I'm moving to the right, and then I get to this location, and boom, I have a pop, I have a jump in my mmap. Okay, so these are, again, this equation is something to write down and to remember on your formula sheet as well. Okay, so which of these relationships is true? Okay, we have a couple of interesting things here, right? Well, one, delta V is equal to F. That's true. dV dx is equal to F. That looks like something else, right? But it's actually dm dx, right, is equal to V. Okay. dV dx is equal to W. That looks kind of right. Okay. dm dx is equal to V. Yeah, that looks right. Okay. Delta M, so these look good. Okay, delta M is equal to mmap. Yes. All right. And this is not right. We already said this is the relationship that we want. Okay. Okay. So just make sure that we calculate the external loadings first. Use the boundary conditions to get the internal shear. All right. That's internal shear. Internal. These are internal shear and internal bending moments. And then we're going to use the differential and integral forms. When I say you don't need to necessarily integrate, what I mean is that once you have the boundary conditions, if you know, like you're going from first order to second order, you can graph it. That's the point of this technique. We're getting there, kind of. We can graph them. And we can create we can also keep track of these concentrated forces or a couple of moments, and we can make shear and bending moment diagrams. Okay, so we're emphasizing drawing the diagrams. So let's think about how we would draw their shear force and bending moment diagram, okay, for the following. Well, we see that we have a couple of moment in there, so we know that we're going to have a jump somewhere in the bending moment. Okay. And the first step, right, is external equilibrium. Okay, so what does that look like? Well, we have reaction forces, right, from the ends, and you're going to see me kind of take some liberties with what a pin and what a roller can do. So sometimes I'll say a roller can pull down, even though it's not really supposed to do that, okay? But you know that these are going to be forces that are applied. These are external ones, so I get to choose. And since that moment is being applied in this direction, I'm going to guess that maybe I want something up over here, and I'm going to guess that I want this pin joint to pull down. Okay. So that's the first step. What's the next step? What's another thing that we do? Yeah.
Internally.
Yeah, so it's probably a good idea to come over here, and on the left side, okay, and of course this is pinned and this is roller, so there can be no moment applied there. So on the left side, I've got this RA coming down, and over here I've got a shear force coming down, and I've got a moment like this. So what I can see at the left side is that M is going to be equal to 0, and I can see that V is going to be equal to minus RA. Okay. On the right side, I have this situation, and again I see that M is equal to 0 and V is equal to minus RB. Okay, I actually didn't really finish though the external loading because I don't know what RA and RB are. Okay, but I can figure that out. RA is equal to RB, right? That's the external equilibrium. And I can also do moments externally, right? So if I take B, then I get that I have an applied moment MO, which is negative, and I have a positive RAL. You know, I'm doing this at B, right, over here. So now I have RA is equal to M naught L. Okay, and now when I do the internal moments, I've got my boundary conditions. Okay. So now let's use the integral forms of our equations that we developed, right? So we have V equals omega, integral of omega dx plus C. Okay. Right, that was the V dx is equal to W in the integral form. Okay, so what is W in this problem? Or what is omega in this problem? W or omega, what is it? W. I guess W is probably what we use. What's the distributed force? 0. Yeah, it's 0. Not absolute 0, I guess, but now we just have a constant. Alright, C. Well, V is equal to C. What does C have to be equal to? On the left side. Or what does V have to be equal to on the left side? Yeah, it's equal to minus RA, right? And what do we say RA is? It says M naught L. So that means that on the left side, it's going to be minus M naught L. M naught over L. Okay. On the right side, what is it equal to? Minus, yeah, minus RB, right? So that means, and we have a relationship for what RB is equal to, RA, so it's also M naught over L. Okay, so minus M naught over L. Alright, oh yes, we did this. No slope, yes, that's it. Okay. Next equation. M is equal to the interval of VX plus another constant. Well, do we have a V? Yeah, we have a V now, right? Okay, and it's with we got a concrete value for it. Right? It's minus M naught over L. So this is it's a constant though. So that what does this mean? That means that M is going to be a first order. So if M is a first order system, then we have we know it's going to be linear, and we have an idea that it's going to have a negative slope. Why does it have a negative slope? Because the V was negative across the whole thing. So that's perplexing. But then what's happening? What is M at the left side, and what's M at the right side? Well, we calculated them out. They're both equal to 0. So now we can say, oh, it's 0 here and it's 0 here. All right, but it has a negative slope. So what in the world are we supposed to do? Well, we need to be a little bit creative. We know what that slope is. That slope is minus M naught L, M naught over L. Okay, so we know that. Okay, and we also So one way to think about this is I can just draw the slope, right? The slope is minus M naught over L. So, once you know where it is, you can just draw that, right? Because that's it has to do that. But we also know that we have this applied moment, right? And this is negative, which means a positive jump in delta M. Okay? So what do? We know that it jumps M naught, and we know it has a constant slope like this, and we know we have a jump, and so this is what happens. All right, the jump happens at the midpoint like that, and this both of these have slope minus M naught over L. Okay. Any questions? So this is you probably didn't, you don't do this in statics, I don't think, right? You didn't do this approach. I don't think they taught dm dx is equal to v and dv dx is equal to w, right? A little bit?
A little bit.
Oh, you did do this.
You got the idea, yeah.
You got the idea. Okay, good. I'm glad you got the idea. Okay, so now you can use this as a graphical technique. Sometimes it's easier, sometimes it's not. But it definitely tells you that it tells you how to remember what, like you're saying, you got the idea so that you know if your answer is wrong, if it doesn't obey these principles. Okay, so that's all for this. There's 2 problems, and then focus on